Yeah, sorry, I changed the talk title at the last minute. The project isn't purely Python-based, so I figured I'd make it a little bit broader. But like Matt said, I'm Brett. I'm a postdoc at UC Berkeley, and I'm going to be talking about the Cesium platform for time series machine learning inference. Stefan here is one of the people on the project. A lot of people probably know him. But this is joint work with a few other people, all at Berkeley. So basically, I'm going to give a quick background of what I mean by time series inference, and then I'm going to talk about the two parts of our project, which are a Python library and a web front end for doing analysis, not on the scripting side of things. I'm going to try to give a little demo, and I'm going to, if I have time, talk a bit about some of the technological challenges that we've faced in developing this kind of hybrid project. So what do I mean by time series data? Probably if you're here, you have some idea already. But basically, what I'm referring to are samples that consist of a lot of observations of the same phenomenon over time. And when I say I want to do inference or machine learning, I'm basically treating each of these collections of samples as a group, and I'm trying to infer sort of group properties about each class or something along those lines. You probably already know this, but just as a couple of motivating scientific examples, a lot of this work is based on one of my PIs, Josh Bloom's research in astronomy. So this is a set of light curve data. It's basically star brightnesses over time. And you can see here that these different classes of stars have different patterns in their brightness. So these are variable brightness stars. The brightness goes up and down over time. And based on the patterns of increases and decreases, you can infer pretty well what type of star you're looking at. So in a lot of cases, we have huge amounts of light curves, and we want to do some sort of automated classification into different groups so that people can look into the data more carefully. Just as a couple of other motivating examples, here's a few EEG signals. So these are from some patients with and without epilepsy. The idea would be to develop a classifier that can distinguish between patients with epilepsy and without, or patients undergoing some sort of seizure or not. This is a pretty standard EEG data set that you can find online, and I'll look into it again in the demo portion. And then we've also done a bit of work with earthquake data analysis, so trying to, say, predict the strength of an earthquake based on the very initial part of the time series of fluctuations. Okay, so I guess one obvious question is, what's hard about time series? Why do we need a special package just for this? So just a few pretty intuitive issues, I guess, are one, the order of the samples matters. So if you tried to train a model where you just treated everything as a big fixed column, you're kind of ignoring a lot of the important temporal relationships in your data. Another problem that you might come across is that you would have uneven length data. So if you have, say, 50 samples from one time series and 2,000 from another, you'd like to be able to do a comparable analysis of these, but it's difficult using standard machine learning tools. A few other things might be you have similar lengths of samples, but actually they're very, the sampling times are very irregular. So if you have data that's on a nice uniform grid, that makes things a lot easier, but in some cases you'll have samples that are collected at very different times, and so you'll need to use kind of a different approach. So the basic idea of our work, and just to clarify, this is not the only way you could do machine learning on time series data, but this is the approach that we're going to talk about in this analysis. So the idea is to featureize your data, to take each time series and compute a collection of feature functions for each sample. And then these feature functions are hopefully going to summarize the important qualities of your data, and you'll be able to build machine learning models using this feature data in the same way that you would for any sort of standard full rectangular data set. And then using these models, you can make predictions, inferences, look at the important variables, things like that. So that's the basic idea. We're going to go from very uneven, ragged time series data. We're going to featureize them all using the same functions, and then we're going to train models on the output. So what kind of features am I talking about here? Some of them are pretty obvious. You would look at the max value, the min value, the mean value. Any sort of standard summary statistic you can come up with would be a good candidate for a feature. But a lot of these are going to be either more complicated, or they're going to come specifically from your domain expertise. So you might know that a very important predictor of some target output is a certain function, and you might want to use that specific function for your data. So we're trying to come up with a mix of these very generic functions and some very domain-specific functions. So just as another simple example, I'm going to talk about the Lom Scargill Method. I don't know if there are many astronomers here, but this is a pretty standard technique in astronomy for trying to do analysis of periodicity power spectra. Basically, in astronomy, there's a lot of unevenly sampled data, very unevenly sampled, and it's difficult to do a standard Fourier-type analysis. So instead, what's commonly done is to fit this sort of sum of sinusoidal functions. We're going to fit it in terms of the least squared residuals. But basically, we're trying to model this noisy, periodic-ish data as some sort of superposition of periodic functions. This is just a mathematical formulation of that kind of model if you prefer formulae. But basically, from a model like this, we can take the estimated period or frequency, we can take the amplitude, and we can use those as features in a machine learning model. Another thing we might do is fit a model like this, and using that model, extract some other kind of downstream features. So for example, in that formula there, phase isn't listed directly, but you can infer it from the relationship between the sine and cosine components. You also might look at the goodness of fit of a model like this. So to say how periodic is my data, that could be an important predictor of the class. And then also just things like you could take any of these and you could apply any arbitrary other transformations to them. So one thing that's commonly done is to try and period fold your data. So you might estimate the period with this Lom Scargill fit, and then you would take your original data, fold it back along that period, and look at how well your period folded data matches. So that's one big part of our work here, is trying to develop a library of featurization techniques, feature functions, that have proven useful in various scientific applications. So the Lom Scargill kind of analysis is one thing that's included, but we're trying to develop a wide variety that are applicable in various domains. Currently, there's a bit of a skew towards astronomy because we have some very specific astronomy use cases that we wanted to reproduce as sort of first examples. But like I said, we're hoping that this will be broadly applicable to all sorts of time series data types. Another thing that we're trying to respect is that there are a lot of different types of time series data, and the kinds of functions that you might use depend a lot on what kind of data you have. So your data could be evenly or unevenly sampled, like I referred to earlier. You could have measurement errors included, and we want to have some functions that take into account how noisy your estimates are. You could have single or multi-channel data, and in some cases, you might have a very complicated model that you think does a really good job of fitting your data, but in cases where your data is too large to apply this, you might want to fall back onto something simpler. So these are all things we're trying to consider in including features in our library. Okay, so just very briefly, the two components, as I mentioned before, of this project are a Python library and a web front end. So the Python library is geared more towards people who have Python experience and they're looking for time series specific techniques to implement. Or it could be people who are actually very proficient in time series analysis, but they're just looking for additional functions for featurization to add to their existing workflow. And then the third case, I guess, would be a user of the web front end, which I'll talk about in a second, who wants to get a little bit more into the details and do some extra Python analysis on the side. The web front end obviously is for people who don't fall into those categories, people who would prefer to have sort of a GUI interface as opposed to a Python programming environment. Probably not many of the people here, but maybe I would be surprised. So just very briefly, the Python library is actually pretty simple. It's the lightweight sort of driver of this web front end. And it basically is just a set of functions to help you featureize your data. Currently, the feature data is being stored in an X-array dataset. For people that you've used X-array before, that might be meaningful, but basically a bit more complex than a pandas data frame. We're trying it out. We'll see how it goes. But the idea is to be able to store the metadata from your features along with the the metadata describing your time series, which you could use as features themselves, along with the features that you've extracted through this Python library. So those are all stored together, class labels, anything you might need in your downstream analysis. And then we also just have a few simple utilities for letting you train models and make predictions, basically just using the built-in scikit-learn model training functions. But now that your data has been rectangularized through this featurized process, hopefully it'll be pretty easy. So the idea with the web front end is there's no coding required. If you have some existing Python code that you'd like to make use of, you can upload that and we will evaluate those functions for you along with whatever built-in feature functions you select from Cesium. Another big driver of this web front end idea was that it should enable you to be able to share your workflows and your analyses quite easily. So this is something that's still a bit in progress, but one feature that we are pretty close to is being able to take an entire workflow developed within the web front end and export it to a Jupyter notebook. So you could either share a view of this web front end, or you could share the underlying Python code that produced it. We'd also like to have views for different sort of scientific domains, kind of like the different feature classes I was talking about before, but maybe more specific models to different kinds of analyses, stuff like that. Okay, so I'm going to briefly switch over to an example, if I can find my mouse. And if I can see the example. So just really briefly, it's quite hard to see, but this is kind of an analysis of the EEG data set that I referred to previously. I want to spend a bit more time on the web front end, but it's basically just a set of calls to these featureize functions. So I'm testing a few different classes of feature functions here. Here are some various built-in functions from the Cesium library, and then here are some functions that I'm defining and passing in myself that I took from a paper that I found that does a similar analysis on this data set. So basically, you can pass in your own custom Python functions, or you can call the functions that we've built in as features. So these are just the sort of, that's another featurization step. And these are just wrappers around certain scikit-learn models in order to make the feature data objects passable into those routines. Sorry that that's a bit brief, but I want to be able to get into the web version of things because we've spent a lot of time on this, and I think it's pretty neat. Hopefully it all goes well. We've rebuilt a lot of this web interface recently, but I think it's coming along quite nicely. Stefan has become a JavaScript wizard, so I think everything's looking pretty good. I'm sorry, I actually can't see this, so I'm just going to briefly go back to mirror mode. Okay, that's quite a bit easier. Okay, so basically we have these 5 tabs here. Things are organized by projects. That's something that you might share with your collaborators. I already have this SciPy demo project, so I'm just going to click this Upload Dataset button. We're working on supporting a lot of different kinds of data types. Right now, it's a bit restrictive, but I'm going to upload these 2 data files. Basically, one is a tar file containing a bunch of time series. Just show you a quick look at what one of those might look like. So basically, these are times, magnitudes, brightnesses of stars, and errors. So like I said before, we support an error column so that you can include those in your analysis. And then there's a header file, which is basically just your list of files, the class labels, and then any kind of metadata you want to attach to those. Okay, so we're going to pick a small subset of the light curve data that I referred to earlier. This is from the Yes, this is from the ASAS All Sky. Is that one? Do you remember what it is? Yeah, who knows? Some sort of astronomy data. I'm not an astronomer. I'm sorry if I gave that impression to anyone. Anyway, so I'm just going to, for the sake of simplicity, I'm going to pick a few features here in this feature tab. We'll go with amplitude, maximum, median, minimum. Keep it simple. So I click Compute Features. This fires off some back-end tasks that are being processed through Celery, and the result gets pushed back to the front end through WebSockets, so you're notified that your featurization is complete. We just started trying to do some kind of visualization stuff. This is an integration with Plotly. Make some nice little scatter plots of your features, one versus another, and the sort of variation among each thing. Obviously, this is a very small toy data set, but just trying to give you a little glimpse of the kinds of analyses you might be able to do. So now that I've created my set of feature data, I'm going to make a model. We'll go with a random forest classifier. We already loaded in all of the class labels, so that's all one object that contains all the information we need to do this analysis. So I'm going to say create model. It's done. And now if I go here, I can say I could either look at the predicted targets for the training data, in which case I would click here, get a little table of results. Again, we're still working on getting some more robust visualization and analysis tools, stuff like that. This is basically just the most fundamental steps of the pipeline that I described. But you could also upload more data that's, say, unlabeled. You could do predictions on that. But that's basically the set of steps. You would upload data, featurize, build a model, and then do prediction. So just very briefly, since I only have a few more minutes, I'm going to talk about some of the kind of technological stumbling blocks and then also nice features that we've come across in this project. So there's just a bunch of obvious Python dependencies, NumPy, SciPy, all that good stuff. Some of the less obvious ones, for our parallelization backend, we've gone through a few different task managers, I guess. Currently we're using Celery, but I'm quite unhappy with it. So we're looking at some other tool for the backend to be able to parallelize the featurization process. For our plots, I just showed you something through Plotly. I have mixed feelings about Plotly so far, but it's definitely pretty cool. Stefan's been working a lot on this cool WebSocket backend. I think he's probably going to give a lightning talk about it soon. But we were using an AJAX polling solution, and now we have this very nice message flow process that as soon as a task is completed on the back end, a message automatically gets pushed to the front end. You should definitely check out that talk if you're around. Using pretty standard database stuff, Postgres. The web front end is all implemented in React and Redux, which seem to be the hottest technologies for this kind of thing at the moment. But basically, a JavaScript-based front end that consumes information served by a Flask server in Python that communicates with our Celery workers that actually dispatch the tasks. We're using Dask in a very sort of lightweight now to organize the computations of related features, but we're looking into maybe using some more of its capabilities soon. We're using Docker actually for allowing users to upload their custom feature code and execute that in a hopefully safe way. And then, as I mentioned, we're using Xarray a bit. We're using netcdf for storage. Just a couple miscellaneous Python project things, I guess. We're using Travis for integration. We are not finished porting our web front-end tests to Selenium yet, so it's kind of a miracle that any of that worked, but that's something that we're working on soon. And for our documentation, I just heard this mentioned at a few different talks that people have had all these issues with read the docs. We have also had a lot of issues with read the docs, and so we've moved away from it. We just automatically build our own docs through Travis now. Yeah, I guess I'll end there. If people have any questions, I would be glad to answer them.
So I have a question.
That's a question.
So it's most talks at SciPy are about a particular library, a particular science experiment. This work is really unique in this context because you guys had to build everything. This is a completely holistic, like the list of technologies back there. That was huge, right, relative to most of the things that we see here. Did you guys have experience in that beforehand? Was that something that was well known to your group, or were there growing pains in there? Can you talk a little bit about that experience of actually deploying a lot of the science out to others in a repeatable fashion?
That is a good question. We definitely did not have enough experience to make that a painless process. We had, as you saw on my technology slide, there are a lot of, I could have listed many more, but a lot of false starts and technologies that we tried to use turned out not to be a good idea. This is actually something that we've run into quite a bit. There don't seem to be a lot of solutions for kind of combining this scientific Python approach with nice looking, presentable web front ends. So I guess if you don't have any interest in time series analysis, but you do have interest in web front ends for scientific analyses, we would also be very interested to talk to you, because this is something that it's taken us a lot of work to get to something that we feel okay about, and I'm sure there's still a lot of things that we're doing quite badly. So yeah, any feedback is very welcome.
So the whole point was about creating features, and you said you had a bunch of features, but you never listed your taxonomy of features that you already are deploying, or are they still a very early work in progress?
I think the total number is around 120 or something like that. I guess I just didn't think that there was time to get too into the specifics. But yeah, a lot of they're almost all features that are lifted from various astronomy use cases, so analysis of light curves and astronomical surveys, things like that.
Okay, so I'm looking in your GitHub repository. Where do I look to find that list?
Great question. There should be a page on the documentation sorry, not in the GitHub repository. That would all be on the, oh no, I skipped the last slide. Yeah, so we also have a website where our docs are hosted, cesium.ml. I believe that the features are all present there, but we might need, we certainly need to improve the documentation of all that. So we're working on kind of integrating the information about the features better into the front end. Right now it's just sort of a big blob of possible features that you might use without much informative information about them.
Okay, I'll look harder.
This is super cool, especially since there's like an astronomy bent. A lot of amateur astronomers are really into light curves because it's something easy that they can do, and they actually add a lot to even the professional astronomy community. Have you like considered sharing this with them, because this might be something that they could use quite easily?
Yeah, I mean, we are definitely open to that. It's all open source. It is shared in a way, but yeah, I think that we are just getting to the stage where we don't feel so bad about the front end that we're willing to actually tell people about it. So yeah, we're definitely looking into ways to sort of do some outreach, find people who want to use it. So far, this is basically just our attempt at making a web front end that can reproduce some analyses that we already know how to do. So looking for new use cases is something that we're really focusing on in the future.
Could you give an example of what the input format would look like for labeled time series data?
Yes, I can do that. I think that I meant to, and I briefly skipped over that. So I think I showed you this one example of what an input light curve would be. The other side of that would be a header file that looks something like this. So basically, file name, oh sorry, that was unlabeled. So here's one with labeled data. Basically just a column that says class or target. It could be a string class label, or it could be some sort of regression target. We currently support both of those. I forgot to mention this as well, but we mostly stick to supervised learning tasks at the moment. I've talked to a bunch of people who are like, well, all of our research really cares about unsupervised learning. So that's something that we're looking into in the future, but just haven't gotten around to yet at this stage. But does that answer your question? Okay.
Thanks.
Yeah.
Okay, we can keep asking more questions, but in the meantime, can we have Demba Ba coming up next? So we're talking about wearables, so just set up, we're talking about wearables. We keep asking questions. If there are any more questions.
Yeah.
Okay, if not, let's give Brett a round of applause.
Do you want to go for